I want to start by saying thank you all for staying to this point in the conference and being part of what I'll call a journey in design. And I'd like to say that I've been to a number of conferences around the world, and this one I find to be the most appealing, and I'll tell you why. It's organized by students, and the university supports the idea with the professors and leaders that are here, but it's the students that make this happen. And so for students that are learning about the process, maybe you're not seniors, maybe you're juniors or sophomores or freshmen even. Maybe you're an architect, because I think there's some architects here. This is a great process because it brings the world together on design. And I can attest to that because I'm official now. I have an official tie. And I understand now I have a tattoo. So this is tattooed here, okay? All right. Okay, so I'm going to talk about tall buildings today. And I'm going to talk about buildings that are inspired by nature and change. And what I mean by change, I mean environmental change, what's happening around us, okay? And I want to talk about the relationship between buildings and the ground, okay, buildings and the ground. And I ask you the question, do we design buildings to be permanent or temporary? Think about that. When you design, do you design buildings to be permanent or temporary? And then I'll ask you, if you're designing it to be permanent, what are you doing to make it resilient and able to test, the time that it sits and also the environment that it sits in, whether it's seismicity or other challenges? Cities are at risk around the world. They're at risk for environmental pollution, air quality, health, and it's related to what we do when we build and operate our buildings. And we have a great responsibility. At SOM, we're designers. We design buildings, but we also design cities. So we start with plans like this. So this is a plan of a large area in Guangzhou, China. And this is an area that is largely a brownfield site. So we have an opportunity to change this place by the way we design. Everything that you see in white, and the images to the right, are new buildings. So the impact is great, but we can make great ideas become real because of these opportunities around the world. Buildings don't have to be tall to be important, right? They can be short buildings that engage with people. So we can use things like graphic design or music to interact with people, right? So it's important to think about the ideas that I share today. They're not necessarily just for very tall buildings. They can be for buildings that are shorter, long span. They could be for bridges, right? So all these things are interconnected. A few years ago in Amsterdam, there was an experiment that was done. And this experiment allowed people to carry a tracking device and walk around the city. And it went on for a few months. And what you see in the map is where people traveled. And they traveled where you would expect them to travel. On sidewalks, roadway systems, places that we define. Places that we define. But the question is, all those places in between, were they absent of life? Probably not. Were they places that we didn't travel as much? Yes, because we defined where people would be in the city. So a couple of questions. First, Are our cities ordered by the streets that manage flows of vehicular and pedestrian movements, where the areas in between are void and absent of life? Should our structures be restricted to regular load paths, defining elements set up on disciplined grids, ignoring the spaces in between, ignoring their contributions only because an order has been imposed upon us, or we have imposed an order? Should structures be designed as static objects, or as objects that are in continuous motion? Should we continue to think of structures two-dimensionally instead of volumetrically? So there's change happening on the planet. There's temperature rise. No one can disagree. Some people say it's natural, others say it's man-made, but nonetheless, we have temperature changes that are happening. They happened in the last century, and they're going to happen again this century at an accelerated rate. So what about materials? You know, how do we use materials to create structures that are more efficient, that might use concrete or steel, but then look at other materials that are created by nature, right? Things that grow, things that had grown that we're using in structures like wood. And this impact is significant. So in the Arctic, there's change that's happening, and not too many people see this, but glaciers are dying, sea levels are rising, ice is melting. There's no doubt, it's happening. The image that you see on the right-hand side of this slide is one of two in the world. It's a seed bank that has every seed known to mankind, just in case. Just in case. So how do we think of that when we design, and how do we change the path of this change in the environment? That's what I would argue is probably one of our most important goals.
Celestial event. No. No words. No words to describe poetry. I should have said the poet. So beautiful. Beautiful. So beautiful. So beautiful. I had no idea. 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 I had no idea.
when we build buildings, big buildings, usually, it takes about 20 years for the operational carbon from HVAC and lighting to overcome the carbon that we put into our buildings the day we build them, right? So for 20 years, the impact on the environment is greatest because of the building itself, not because of the operation. So we need to think about this when we design. And we've started to. And if you go to our website at SOM, you'll find a program. And it's the first step, you know, it's an incremental step, but this program will allow you to calculate carbon in the structure of your building. Not just at the time that you build it, but over its life, all right? And there are three major components to this. The first is material, so concrete and rebar. The second is construction. And the third is what we call probabilistic damage. And you can define a building over its service life. In this case, the building has a life of 50 years. And it's in an area of seismicity. It's high. The winds are moderate. But what you can do with this program is that based on a database of hundreds of buildings that SOM has designed, the material quantities that were required for those towers are embedded in this program. So what you can do is tell it very simple things like the number of stories, the number of basements, the type of structure you want to use, concrete, steel, wood, metal framing, whatever. And you can tell it what type of seismic system it has, because seismic systems are contingent on damage, right? They're interconnected. And seismic systems, if they're done right, they make the building perform better. There's less repair. There's less reconstruction. And guess what? There's less carbon in the end. So you can take this idea and you can apply different concepts to it, and you can calculate the material in your building and also the carbon in the building. We think this is important. We think someday this is going to be in the building code. So it's not going to just be safety. It's going to be things like carbon in the environment, okay? So this is a first step at calculating this. And I think at the universities and practice, we're going to see a lot more of this in time. Okay, so nature's a really interesting thing. So bamboo, there's a lot of bamboo around and here. And if you look carefully at bamboo, it has a series of rings that happen over the height of the bamboo, right? They're not evenly spaced. Look at it carefully. They're closer at the bottom. They get more separated toward the mid-height, and then they'll close again at the top. The bands are diaphragms. The bamboo's hollow. So the diaphragm is there to protect the walls of the bamboo from buckling under wind load, mostly, right? So wind loads are applied. There's some gravity load. Wind loads are applied. Demand is on the outside of the bamboo culm. And those diaphragms are there to protect the walls from buckling. What's interesting about it is that it's not random. You can actually mathematically predict the placement of those rings. And there's an example of an equation that you can use to do that. And it's not just the placement of the diaphragms, it's the wall thickness and it's the diameter of the culm itself. But if you look carefully at the equation, it's a quadratic. When you plot the moment diagram for a fixed base cantilever, for those that are structural engineers here, and you apply a constant load, the moment diagram looks like this. And it's the same relationship of the spacing of, in this case, the diameter, the size of the diameter, but the spacing of the diaphragms or the wall thickness is all based on the same principle. It makes sense that a cantilever should be, the mathematics of a cantilever in the bending moment should be buried inside of things like this, like the bamboo, right? So now what do we do with this? How do we apply it? Well, if you think about a building, you might think about strong diaphragms at certain points. Outriggers, we call them outrigger trusses, walls that connect the inside to the outside to resist lateral loads, wind, seismic. And you can take buildings and break them down into an idea where you have spacing of diaphragms that's not even, but it's closer at the bottom. It might open up toward the mid-height and then close again near the top. And the reason why it closes in bamboo is because the geometry of the comb is smaller. So there's a proportional relationship between the spacing of the diaphragm and the diameter. So this was a competition that we entered. The building was built. This is in Beijing, China. It's called the China World Trade Center project. The building was built. It doesn't look exactly like this. And the concept was actually not used in the end for the final design. But nonetheless, we found that it was very efficient to tie the outside frame to the inner core with this strong diaphragm to get more efficiency in the structure, more efficiency out of the resistance relative to the amount of material that we're using. So this appears in other places. Okay, it's not just it's not just in bamboo, but it's here. It's in the tail of the dragonfly, right? Same problem. It's a hollow section. The diaphragms are there to prevent buckling of the walls, to keep the stem intact. And you can take these ideas and build on them, right? When I was many of you are maybe finishing college or you're in graduate school or have recently finished graduate school. When I was only a few years out of graduate school, I had the opportunity to design this building. And this is in China. This is the Jinmao Tower. At the time, it was the third tallest building in the world. It's 420 meters tall. And it used concrete and it used steel, we think, in a pretty effective way. It's a very tall building, a very slender building. And what we did is we connected the core to the outside with these outrigger trusses. Okay, big steel trusses. 1, 2, 3, 2-story levels in the height of the building. And what we did is we connected the central core to the outside columns with these big steel trusses. And guess what? We found a problem. We had an idea. We found a problem. That if you built the building the way you see it with the concrete core and the big concrete columns, and you did nothing, you just built the building and you connected the trusses, the creep, the shrinkage, and the elastic shortening of the building itself would rip the trusses apart because the trusses were so stiff for wind and seismic to connect, right? You would actually rip them apart. So we had a problem. So popsicle sticks. Okay, we had bridge models yesterday, right? Guess what? They're the wood dolls. Okay? So these are popsicle sticks, tongue depressors. There's the big column. There's the core wall. And the key was the slots in the head of the truss to allow the truss to move like a mechanism during construction. All right? So during construction, it would freely move, no bending moment, slide, rotate, okay? And there you have it. There you have a free-moving mechanism, no force. Okay, so this is a Saturday night project with my daughter. My daughter was the one, you saw the film, the piece from the Arctic? That's her film. So she's an artist. And so Ashraf yesterday talked about art, right, and how it might influence design. And, you know, we think about this a lot, and not just in our family, but also in our practice. And art matters because there's a message in art, and what you see in art helps us make decisions that may not otherwise be accessible, you know. And so these were kind of the early days of this idea. It started with the popsicle sticks and the pins, and it became this. So there's a working drawing. The shop floor, prefabrication, the piece at the site before it was erected. This is one of the connections here at the bottom. For those that are over here, one of the connections, and there's a man standing next to it, one of our site engineers. And you could see the hole for the pins, all right? And then the piece in place. And so we were able to free the trusses up with the pins. Then we put the bolts in later on, right? And the building went into operation. And the view you see here is the view in the atrium of the Hyatt Hotel, which is still, I think, the tallest atrium in a hotel in the world. And you could see the columns in the bottom that were linked together to the core and the scale of those columns. So, you know, it's big stuff, but it comes from these like basic ideas. Those truss models that people created and tested are a really good example of this. Start small. Start to look at how load paths work, and all of a sudden it becomes something like this. Or it becomes a long span bridge. Okay, so people have had fun with this building, all right? I would never do this, but apparently people do this kind of stuff. So it's a building that people can relate to, right? Whether you climb it or see it or whatever. And we've done this in other places around the world. So this is a Sears Tower. And at Willis Tower, I guess we call it, I'm going to always call it the Sears Tower, but it's the Willis Tower. At the very top at the observation level, we designed these glass boxes. I guess we call it the ledge, right? So there's a little girl, there's the city. I mean, it's kind of scary. I don't know. I got out on one of the, I don't know if anybody's done this yet. I got out on one of these, and I'll tell you, it was like, whoa, this is really, this is not the way to see the city. This is way too scary. In Kobe, Japan in 1995, it was about the same time as Jinmao, around the same time. Big earthquake, right? Many of us study this earthquake, and the reason why this earthquake was important was because it tested a lot of buildings. Like a lot of major buildings were disrupted by the earthquake. This is City Hall, the original City Hall in Kobe, Japan. And you notice that floor is missing. It's gone. And I toured this area about a week after the earthquake, and I was heading to Shanghai for Jinmao, but I was able to go here to this place. I started thinking about this, and I thought, well, can we do a better job? Are buildings behaving naturally in an earthquake? And then, around the same time, I went to Santiago. There was a similar kind of conference like this, but it was with architects and engineers. And after the conference was over, one of the architects had volunteered to take whomever wanted to go from the speaker group to the Isle of Chiloé, which is way south. Okay, it's way, way south. And we went to this island, and this is what we found. It was a fishing village for the most part, and some of you may have been to this place. Indigenous architecture, just beautiful residential architecture that, in a lot of cases, people built on their own. There are two people in this image. There's a man and a woman. The man that's standing there is Richard Tomasetti. Richard Tomasetti is Thornton Tomasetti. He was one of the founding members. We traveled together in a car. We're competitors, right? We're competitors. It was those two people, Richard and what was to be his wife, soon after this trip, myself and an architect, and we spent the entire weekend together talking about life, not about how we compete against each other, but about life. And we talked about these places that we visited. And we visited this church. And this church survived the great earthquake of 1960, where my understanding is that the ground moved like the ocean. The engineers that were there locally said that they could see the wave really moving the ground by meters, and telephone poles and light poles rotating and touching the ground because the rotation was so high. The earthquake was huge. These churches, these Jesuit churches, did really well in the earthquake. And I started to think, well, why would these churches do so well? I went up into the attic of this. You could get inside and see all the trusses inside the top of the church. All the connections were done like this, with wood dowels, not with metal fasteners, not with straps, not with some type of heavy plates. They were all done with these wood dowels. And I started to think that you know, maybe the wood dowels are the reason why the building is still there. And I started to think that the joints probably rotated and slid. And the wood dowel is a kind of a fixed connection, but not. Like if you twist the wood dowel, it's fixed in the beginning, and all of a sudden you can twist it. If it overcomes the friction, it rotates. I started to think, that's it. That's the reason why these buildings have survived. That's the reason why buildings in Japan and China and all these places have survived great earthquakes, is because of joints like this. So then I started thinking about our buildings. In seismic events, what about this building? You know, what about this frame? It's not natural. It's all perpendicular. The beams and the columns are all locked. So what happens when you get a big earthquake? Well, you get a lot of damage. The joints aren't natural. Same thing with braced frames. We tried to stiffen the frames, make them more ductile, but we're still going to get a lot of damage in a big earthquake. So what about your body? You know, your joints in the body. And the joints in your body are controlled by ligaments and muscles, right? But they're not free. They don't just spin, right? There's restraint. You can move in many directions, but there's still restraint. The restraint comes from other things like the tendons and the muscles. So I started to think, what if you could create buildings with joints that are kind of like your body? So instead of straight joints, have curved joints. So plates that are curved. And guess what? Maybe use a pin in the center. Put a pin, the wood dowel, but make it steel. Put it through the center and let it rotate about the pin. Only taking shear, no bending moment. The bending moment is taken back here. But don't fix it. Put it in a curved plate system with a friction material in between it and long slotted holes. These are long slotted holes. And then clamp it. So it's fixed for most of its life. Days like today, right? Nice weather, a little bit of wind. But when a big earthquake comes, guess what? It's going to rotate. But not freely. It's going to dissipate energy. You're going to dissipate the energy through heat in the joint that has this almost like a brake material, like a friction material that you can calculate when it's going to slip and under what load, how far is it going to rotate, because you know how much the building is going to move, right? You can calculate how far the building is going to move, gets back into the joint, into the rotation of the joint, so you know how long the slots need to be. So it comes from just raw thinking, right? So I woke up, well, probably wasn't sleeping. It was the middle of the night, and I quick grabbed I have one of these notebooks that maybe some of you have seen me carrying around. I drew this diagram. I thought, you know, what if we put a hole in the beam and we had a curved plate, put a pin in it, used conventional building materials, and then tried to figure out how it would behave, and then create something that maybe is different, right? So the first time that, I don't know, I know at our firm we've never done this before, but we figured, well, we'll just try it. We submitted for a US patent, just to try, just to see, is it a new idea? And after a couple of years, it took that long, we actually got a patent on this. And it's because, I think, because it redefines how we might think about these types of joints in seismic events. So joints might look like this, frames might look like this in the future, a lot different than that, you know, the perpendicular connections that you see in a lot of our building frames today. So it really is trying to take these building parts and use them to our advantage. So the pin in the web, you need to restrain it, clamp the joint, allow it to rotate once the demand is really high. Protect the column, right? You want to protect the column. So today, we dissipate energy typically in the beam itself, and we damage it, we yield it. Hopefully we don't fracture it, but it protects the column. It keeps the building up and keeps people safe. But this is trying to keep the building elastic in time. Like, you know, you don't want any plastic behavior. You're trying to make it elastic. So then you start thinking, well, you got an idea, but is it an original idea, and can you do another idea? So we started thinking about other things and like other systems. So here's a brace, right? Here's a link, and I'll show you a little bit more about those. So this is a braced frame that has a friction joint in the middle part, and then also on the joints. Okay, you see that? And this joint's a rotation joint. It's a little different than the beam end joint, right? If you look up close, it's just allowing it to move when you want it to move. And this takes, again, straightforward building parts, a pin through the web of the beam, and then bolts, and it has the long slotted hole in there so it can rotate in the event. And then when you get these displacements that the brace, I mean, a lot of times in buildings, the brace in a seismic event is not a great thing. It's not very ductile. So we need to come up with a way to keep buildings stiff, but then also allow them to slide or dissipate energy in a major event. So it doesn't have to be just in steel buildings either. You can do it in concrete buildings. So here's a shear wall building. We do a lot of shear wall buildings, residential buildings, office buildings. Maybe the link beams have these kinds of joints in them, right, that are like a butterfly joint. So it might look like this. So you have two joints that are slotted in an opposing way with a pin through the center. You clamp it so it stays fixed during the moderate events. And then when you get a big event, it dissipates the energy. But again, you don't damage the structure. You're trying to protect it. So a few years ago, we had an opportunity for a competition. And just so you know, in our practice, if you can win 1 out of 5 competitions, you're doing really well. So 20%, remember that 20% rule. If you could get 20% of them, you're doing really well. Well, we competed for this. This is the Transbay Tower in San Francisco. We didn't win. We lost. And the reason why we lost is because it was a developer-led competition, and the developer put $140 million US for the site, for that tower. And the idea was you give that money to the city, and they use it to develop a train station and bus station. The winning team put up $340 million. We lost. You can't compete. Like, there's the commercial value. There's just no way, right? In the end, my understanding is that, and the building is basically finished now. It's almost finished. It was done by Caesar Pelli. My understanding is the developer gave about $140 million for the site in the end. So life could have been different if our tower was there, but it's not. But what we did is we learned a lot about structural behavior and how you might apply different ideas to structures. And one of the things that we studied was the hurricane. You know, the hurricane is something that or the typhoon, we look at it and plan. We watch it on the news or we watch it on the internet. And the hurricane is really interesting because when you get close to the eye of the hurricane, the forces are very, very high. And as you get out toward the end, they get less and less and less. So we started thinking, well, instead of it being an applied force, what if it's a resisting force? And what if you took the hurricane and you stood it vertically, or maybe you spun it around volumetrically? So you had high resistance toward the eye, right, and less resistance where the arm is way out. And it's a logarithmic spiral, so it's not a linear relationship. But the hurricane is mathematically predictable. It's not random, right? So we set off to do that. We started to think about it. The hurricane is, the mathematics is present in things like this seed that you see here. This seed is called the stork's bill. And the stork's bill has a little, almost like fish hooks at the bottom of it. And this was actually on my wife's running shoe in Northern California. So this is like, it's a real thing. This is actually a photograph of it. And what it does is when it dries like, it corkscrews in the ground, and it dries like the golden spiral, It keeps screwing itself into the ground. Why? Because the seed, it makes sure that the seed gets planted, right? That the seed gets into the ground, it gets planted, and it grows. So this is in other places, you know, spider webs, autoshell. Mitchell, in the early 1900s, defined the perfect cantilever. It looks like this: 2 points of support with a point load. It's not a straight line. The cantilever is not a straight stick. So the building itself, if we were to design a pure cantilever with a load at the top of it, it actually would look like that. That's the most efficient structural form, the most efficient structural frame for the cantilever. It's not a straight line. So you wonder, it's like, well, why don't they look like this? Well, there are other ways, there are other things that happen that gives us clues to this. So when my girls, I have 3 daughters, okay, and when my middle daughter, before each one of them started college, I said to the girls, I said, look, we should go on a trip, okay, not a vacation, like not a vacation trip, and not like a torture trip, like not a trip where you got like, you know, you drag somebody around and say, you got to look at this, but go to cities around the world that are interesting, you know, and try to see art and architecture, maybe a little engineering, you know. So we went to this place. This is the Eiffel Tower in Paris. And we got to this plaza and walked onto the plaza, and I said to my daughter, I said, Ellen, I said, look, if you want to see this building, really want to see the Eiffel Tower, we got to walk the stairs. Okay, she's like, oh, the kids call me Pops. Okay, Pops. They're like, oh, come on, there's no way. Well, I don't want to walk the tower. I said, no, this is how we have to do it. We got to just do it. Oh, okay. So we go to the stair. That's the entrance to the stair. There. You see that right over there? That's the entrance to the stair. And we walk all the way up to the first landing, and it's a long walk. But, you know, it's kind of good because you can see the structure. There's some history along the way. It's pretty nice experience, right? We get to the platform, and we look down. This is the line to the elevator, okay? These people are in line to the elevator. It's not a straight line. They're in the shape of a golden spiral. Okay, so we, inside of us, are also thinking like the plants and the seeds. It makes sense, right? It's not exact, but I bet you if you put mathematics on this, you get pretty close. This is the position of least energy of people standing in line for an elevator, right? So you got to think about this because it's not something that just randomly happens. I mean, it's happening all around us, right? So we're trying to figure out how can you take this now and apply it to a building. So we were designing this building. This is a friend of mine. He's a pastor. He's a minister for a Presbyterian. It's a theological seminary in Northern California. Okay, so this is part of the response that he gave to his incoming students for one of the years. He said, and oh, by the way, I met him at a party, and he said, well, what are you doing? What are you working on? I said, well, I don't know. We're working on this building in San Francisco. It's got some pretty interesting ideas. We're thinking about the hurricane. We're thinking about design, resistance, and so forth. I said, well, tell me a little bit more about it. I said, well, we think that there's a relationship between the hurricane and the building if we design it properly. And so I told him the story about what we were doing. And he said to the students, he said, what if we could develop strong, flexible, responsive, adaptive, sustainable human buildings based on the intrinsic architecture of the hurricane. Buildings that exist in harmony with, instead of trying to resist and stand up against and conquer. So coexistence, right? The powerful creative forces that might otherwise threaten and endanger us. Why can't we do that, right? So he was challenging his students to think about this relationship. We were trying to figure out how to take this idea and apply it to the building, right? So we took this perfect cantilever, and as a structural engineer, you know, that would be the shape of the building that we would have proposed, like that bulbous shape. But our architects are like, no, we don't want anything to do with that. There's no way we're going to make a building that looks like this, right? So we made a less perfect solution, and we took an excerpt, we took part of the idea, and we created a structure that was well resolved, created an opening at the base where people would go to the train. We'd create density of structure that was tighter at the base, and then as it opened up toward the top, it became much more open. And it's all related to demand. So seismic demand, wind demand, and it makes sense. We found that this structure was very efficient, and it was beautiful, even with a complex form. So it's not a square shape. I mean, this building is changing shape over its height because the bottom, it's more organized and regular. It's an office building. At the top, it's residential and hotel. So more daylight, more windows, that kind of stuff. But you can look at it and you can say, wow, you know, this is a pretty well-resolved structure. And it uses all those principles that I showed you. There's an idea that we've been studying, and it's called emergence with an E. And here are some examples of emergence. Termite mounds, like termites working together to create supercooled termite colony areas, right? Grains of sand, impacted by things like wind, honeycombs, birds in flight. You know, why are birds flying together? Why in migration times, why are birds changing position and so forth? It's because of least energy, right? There's a relationship that makes common elements, whether it's birds or termites or sand, common elements, much more powerful when they're working together rather than being alone, okay? So another example of that is cities. Another example is this place right here, right? This is an example of emergence because all of us are much more powerful because we're working together than we would be on our own. There's no doubt about it. So these are ways to think about it. So how does emergence, like how does that relate to a building, right? How does it relate to this interaction that exists on this planet, right, between people? So this group of people are far more powerful working together than they would be on their own. And in places that we can't see with the naked eye, we need help. We need iron filings to sort of help us understand magnetic fields. But this is the place where the least energy exists of those metal filings in that magnetic field. Now, if we took this and we looked at buildings and we looked at boundary conditions like supports for columns at the bottom, okay, at the bottom of this diagram, and we applied a load, what you'd find is that if you don't define a line for a column and a beam, you just create a surface and you apply that load, you find that a frame emerges out of that that looks pretty organic. It's not something you could build right away. The red is areas of high demand, blue, least demand. But it's something you can interpret, right? So you might take it and look at it as a steel structure and interpret it in a way today. In the future, we might be able to do this, right? But today, we have to interpret it. But nonetheless, it's getting closer to the most optimal solution for that lateral load, for that type of shape of structure. So this idea of load path, growth, mathematics, all leads to different types of architecture. So we're finding that in buildings that typically had concentric braced frames, in fact, they're more efficient if they have what we call a high belt frame. So the frame, instead of being 50-50 even, it's 75% to the node point and then 25%. 75% and 25%. This is the theoretical solution for a lateral load. You can see it. The lateral loads are on the side, 2 points of support. But it's not architecture. You know, it's structure. It's just the first step. So what we did is we interpreted this. We stretched it. We stretched the building. We created shapes. We took the analysis from the beginning, and this is a density analysis which uses those points of support. It optimizes the placement of material, sort of like the emergence theory idea, right? It's the place of least least energy, greatest resistance, but it's not a conventional cross-braced frame. And it looks different. It looks different. You're surprised. It's like, well, we've been doing this for hundreds of years. We've been thinking of structures. Why would all of a sudden it be different? Well, it's because of the boundary conditions that we're setting up. It's the fact that we're not defining it ourselves in the beginning. We're trying to use analysis techniques to help let these ideas come out. And then you can take it and you can apply it to something you might build. So there's a concrete core and a steel frame and steel framing. So it's something you could actually build. So this frame at the outside is much more organic than that typical cross-braced frame that was very efficient and that we used for a long, long time in buildings. And what's really important when you're designing these buildings, these tall buildings, is that I call it stiffness and softness, okay? Stiffness, think about it, stiffness and softness. Stiffness, because during the normal life of a building, it's got to be stiff to resist wind and earthquakes, moderate earthquakes. But when you get a big earthquake, you want to dissipate the energy through these links. So what we've done is we've combined both systems together. So you have stiff systems they're largely axial loaded members, no bending, and then we have ductile elements to dissipate the energy. So buildings in the future might look a lot different than they do today, right? So there's the Hancock building in Chicago on the left-hand side, and there's the CITIC Tower in Shenzhen, China on the right. Both very good buildings, but the building on the left is of a time about 40 years ago, maybe more now, and then there's a building that's inspired by these techniques. Now, it's not just tall buildings. You can take these ideas and turn them on the horizontal, right? So bridges that we build all around the world are very efficient. The Warren Truss, there are many different types. This is an example. Very good truss. This is at LAX. This is in Los Angeles. And what the airport asked us to do, they said, look, we have all these bridges, these pedestrian bridges. Can you guys please help us with some new ideas? The Olympics was coming. It looks like it's coming later, but it's coming. We're going to do all this upgrades. We're going to change these things. So what can you do? We took the tall building and we flipped it on its side, and then we rotated about a center point. So this is a span from support to support. There's the tall building base. First projecting one way, and then mirrored and projecting the other way, okay? So about a central axis. So right there, we're mirroring the tall building. And there's the bracing system that's not concentric. And we found that we could actually reduce the amount of material by a lot by using this technique of having a bracing system that was offset by this 25%, 75% rule. Now you can imagine that we can use this in floor trusses for buildings, right? It doesn't have to be in bridges. So typically we might have a V-shaped panel system in our floor trusses. Well, maybe in the future it's going to be a panel system that's 75%, 25%, and we're going to use less material. Think about it. This is a shape that's an elliptical shape. This is an idea that might use concrete, an idea that might use steel, but you can see this organic idea about how you make that span work based on the principles of the tall building. So here's a model of it. It's not built. Not yet. But these ideas might lead to other ideas. So we were pretty excited about kind of this discovery about how you could take the tall building and make it into a bridge. You can make it into art. Yeah? So it doesn't have to be a building. These are net structures by Janet Eckelman. And if you look at the internet, and maybe there's some examples here in South America, she is using ropes, fishing ropes and fishing nets to create these beautiful structures. And this is a project that we did with her in West Hollywood. And it uses that same Mitchell truss idea, only on a horizontal. And there are 4 net support points where we used ropes to tie between two buildings, and then we suspended these nets from inside. And so what you're seeing is different lighting conditions of that sculpture, and it's up on the hillside in West Hollywood. It's sort of, if you look toward the Hollywood sign, it's up in the hills there. So at nighttime, you could actually see this now. But it uses the same principles that we were talking about earlier. Now, how do you apply it to things that may happen a lot? Okay, so here's a building here's a building in California, in San Francisco. Here's the Bay. It's a residential building. It's a condo building. Pretty simple design in terms of a square floor plan. Not super tall, you know, not super tall, maybe about 25, 26 stories tall. But we started to think about these principles in the tall building and taking the plan that's really regular with a core, walls, and a flat slab that spans between the core and the columns. We use this a lot in residential buildings. The shape might be different than this, but a lot of times we use a concrete core wall system and concrete columns and a flat slab. And a lot of times we'll use pre-stress. We'll pre-stress the slab. In this case, it's post-tension, so we pull the strands after it's been placed. We started to think, we've been doing this forever. We've been spanning post-tension cables in a straight line, okay? And sometimes we gather them, we group them, but we can never do better. Like we try to reduce the material and the post-tensioning, and for whatever, try and try. We try so hard. We engineer every half a meter. We're so careful on placement. We just cannot reduce the amount of cables. We started to think, well, maybe we got it wrong. Maybe we're not quite right on load path. And if you look at this last diagram, it's like a flower. It takes the post-tensioning and it flares it in plan. And it's not necessarily a straight line between support. So it's a curved line. And what we tried to do is we tried to map the stress diagram in plan and place the cables in a way that controlled displacement. So the blue is a lot of displacement, and the red is less in this diagram. And place the cables in a way that are really efficient. So it uses those same kinds of principles by mapping the stress in the slabs. So we think that using cables that are looking like this, and we can do this already today, because those cables are flexible, right? And we still drape the cables up and down, but maybe we drape them up and down and we do them on a curve rather than a straight line. We found in this slab, and this building's under construction, so hopefully I'll come back and tell you it's very successful. I don't know, we'll see. 25% reduction in post-tensioning cables. It's a big deal if you think about the environment, because then we have to make so many cables, right, and use so much natural resources. But it's all based on the same principles that I showed you earlier.
Hello there. Hi there. Hi. Oh, thank you. Wait, okay. Hold these. Milkshakes. There we go.
How many milkshakes did you buy?
Oh, one strawberry, one vanilla, and one chocolate.
Is that what you ordered, Jack?
One of each.
Yeah, but your food still needs to cook by the rain or
I know that. I'm just saying a bit. I know that. Yeah, I'm really sorry. But can we get a move on? That's fucking good, then. Nothing better than fucking McDonald's milkshake. Cheers, mate, for doing this. Cheers, mate, for doing this. Appreciate it. That's everything. Wicked. Drive. Let's go. Stay outside.
My love and I. A ship there is, and she sails the sea. She's loaded down as deep may be, but not so deep as the love I'm in. I know not if I'll sink or swim.
So, awareness, right? I mean, what we buy, what we do, we sit in cars and we let the cars run, yeah? And we're not aware in the way we should be. And it gets into design as well. So this is an example of maybe everyday life, right? But I think what's important is that when we talk about designing these cities, we should be thinking about these principles all the time. So all those buildings in white will be built someday, right? So if we do it right, we can make a difference. If we do it wrong, if we keep doing it the way we've been doing it, then I would say that our chances are slim that we're going to make the corrections that we hope to do. Cities are filled with data, right? iPhones. Everybody's got, iPhone or Samsung, whatever. It's filled with data. So how can we use data in a way that helps us with our buildings? So I call this sensory fields. I call this a mechanism to look at a place and understand things like winds, earthquakes. What's the magnitude of the earthquake? Which direction is it coming, right? And can we use this information to inform our buildings in a way that's really smart? So this is San Francisco, and we're actually making progress now. We can actually detect the earthquake coming, not necessarily minutes before it happens, but in the order of seconds, but we can at least react, right? We're starting to be able to do that. But the idea might be that we tie the information, the data, to our analysis models, right? We spend a lot of time analyzing buildings as engineers, and then we create drawings. We have our drawings, and that's what survives. The analysis models, who knows? Okay, it's on a disk, and then we can't run the disk. We don't have the program anymore. We don't, So the point is, can we take our analysis models and tie them to the ground or to the wind and try to understand where the forces are going to be in an interactive way, right? Because that's the way we're analyzing the building to begin with. We're looking at magnitude and direction, and we're sizing our building in accordance with magnitude and direction. So is there a way to make our analysis models interact, and then can we tell our building what to do? So that's the idea. So maybe we can take buildings with the idea of stored energy. Yeah, Tesla's doing it. Forget about the car for a minute. They're an energy company. They're not a car. Everyone thinks they're automobiles. I believe the automobile is this much of that organization. It's all about energy, right? And what they're doing is they're talking about stored energy. And stored energy helps us with things like this, like magnetic levitation, right? Because everybody's worried in the past, like what happens if I'm trying to move something around and the power goes off? I got to start a generator, whatever. If I have stored energy, I can change the behavior of my building right away. I don't have to wait, and I can be really super confident of it. So maybe we can displace our buildings, move them in a way that's controlled, not just free, but by using techniques like stored energy to move a building away from the ground temporarily. Sounds kind of crazy, but temporarily, well, you have big ground motion. Maybe.